Okay, here we are, chapter 12. This chapter is on matter, is the title of the chapter, but we're going to spend most of the chapter talking about solids because the second chapter in this unit is about fluids, and both liquids and gases both qualify as being fluids. So we've got just a little two-chapter unit here, chapter 12 and chapter 13, basically about the states of matter and their characteristics and how this affects their motion, and their other properties that we deal with on a regular basis. So here we go with chapter 12. So what states of matter do we have? We were all learned in grade school about solids, liquids, and gases. Those were the three states of matter. As we go to more extreme situations of temperature and density, you can get other forms as well. There's something beyond a gas that's called a plasma. Basically, you take a gas and you rip the electrons away from the nuclei, and it's all in one big um, mixture, and we call that a plasma. And then on the other end, below solid, there's something called a Bose-Einstein condensate. But we're really not going to focus on those two exotic forms of matter. We're going to focus on the solids, liquids, and gases, talk about their differences and how we came up with our understanding of them in the first place. So a little bit of history. Way back in the day, 2,500, almost 2,500 years ago, there was a Greek natural philosopher, which is what they called their scientists at the time. And his name was Democritus, and he came up with this idea that if you cut something and cut it in half, you get two smaller pieces, and you cut it in half, you get two smaller pieces. You take the half, you cut it in half, and so on and so forth. Eventually, you'll get something that he said, he couldn't do this. He didn't have a microscope. Um, but he said eventually you get a piece that was so small that if you cut it in half, it was no longer that same stuff that you started with, right? His idea was partly a philosophical argument that you have to get to a point where something is so small that if you cut it in half, you don't have the same thing anymore. And so he came up with a word for that. He said the smallest thing that is still that thing, like the smallest piece of gold that still has the properties of gold, or the smallest piece of iron that still has the properties of iron, is an atom of gold or an atom of iron. So that's actually what the word atom means, the smallest possible piece, which is no longer what it means to us today, but we'll get to that in a little bit. That was his idea. But then along came another natural philosopher named Aristotle. Remember, in the before the Common Era, BC, the numbers count down, right? So anyway, in Aristotle's day, 40 years later, Aristotle came up with this idea of looking at matter a little differently. And his idea was that we could look at everything as being a mixture of earth, fire, water, and wind. And that became very popular and very accepted, as were many of Aristotle's ideas in a lot of areas of science. This earth, fire, water, and wind is not unique to Aristotle. There are many other cultures that have come up with this as a basic understanding of the world and the materials in the world, right? You mix a little bit of water with earth and you get mud, right? You mix a little bit of earth with wind and you get a dust storm. You mix a little bit of fire with that mud and you can drive the water back out of the earth and make dry dirt again. And of course, part of Aristotle's idea was that we as humans were the pinnacle of nature, right? And so we were actually a combination of all four of these things, right? We know that when people die, their bodies decompose back into dirt. So that's it's clear that we have an aspect of earth to us. We know we have to drink water or we will not survive. One of the most critical things that our bodies need to continue living. But the most critical is the wind, right? We must have air to keep breathing. And if you cover somebody's mouth and nose long enough, you will cause them to stop living because you will deny them that wind that they need in order to function. And so that leaves us with fire. And again, if we have experience in life, we know that living organisms are warm, not plants necessarily, but animals and humans, living organisms are warm. And when they die, they go back to being the same temperature as the environment, room temperature, as we call it sometimes. So there is warmth inside of us. So we have this combination somehow of earth, fire, water, and wind. And that was Aristotle's idea, and it held for a long time. But as they continued to study matter, as they tried again in this grand cyclical process of trying to understand the earth, try to understand nature around us so that we can practically use it to help our lives, as we tried to figure out different uses and functions for metals and other materials, this categorization of Aristotle's just wasn't good enough. It wasn't specific enough. So as they did more and more work, they found that there were different types of material. Many of them were solids, and that matter was chunky, and there were unique characteristics to different types of matter, right? They were able to isolate copper and iron and some other metals and study their characteristics. And, according to Aristotle, copper and iron would both be earth, maybe earth that was modified by some fire. But they are different from one another. They have different characteristics, and they can be shaped differently. And so we started to arrive at what eventually would become the periodic table of the elements, which was not organized based on protons, neutrons, and electrons, as is sometimes erroneously implied in a chemistry classroom. It was arranged based on the characteristics of these materials. And you see some of those things. We'll talk about this in a little bit, but copper, silver, and gold have a very similar set of characteristics, and that's why they were all put in this same column. Because of those characteristics. It was a way of classifying materials. And later on, we figured out that those characteristics were because of underlying structure of the protons and electrons, but that was not understood at the time the periodic table was developed 200 years ago. So we are able to ultimately to classify things into roughly 100 elements. Now they are trying to create additional elements in laboratories, and they are successful, but many of those elements do not last for a very long period of time. So uranium is the largest naturally occurring element, and it's element number 92. So really around 100 elements, and the first few artificial ones that they created have longer half-lives than the ones they're creating now. They're up into the hundred and teens, which really don't last for very long. So anyway, we came up with these elements, the 100 elements, and if you've taken a chemistry class, you've been taught a lot about that. But even that was not good enough, right? And so now we get to the point where Democritus's idea of the atom being the smallest breaks down. It actually fits very well with the periodic table and the elements, right? The smallest piece of gold that is still gold, the smallest piece of lithium that's still lithium is an atom of lithium. And if you go smaller than that, it's no longer lithium. But it is not the smallest that can be. It's the smallest that an element, smallest piece you can have that is an element and has the properties of that particular element. So as you learn in chemistry, there was something called the Dalton's billiard ball model of the atom, which basically says it's just a hard, solid sphere that's made of the same stuff because it's as small as you can get. It's the building block of life, building block of all nature. But around 100 years ago, around the turn of the 20th century, they figured out that that was not actually the case. Just before the turn of the 20th century, they discovered the electron, and then the proton right about that time, and the neutron a couple of decades later. But the proton, neutron, and the electron are what make up these atoms. That's what's inside of them. And that's another layer of size, another layer of smallness of matter. Again, we've spent the first 11 chapters of this course really focusing on motion and forces which cause motion, and now we're looking at the other part of what physics is. Physics is the study of matter and energy. We spent a lot of time on energy already. Now we're spending more time here on matter and the structure of it. So protons, neutrons, and electrons are even smaller than the atoms, and the chemistry, introduction to chemistry, is all about how those protons, neutrons, and electrons fit together to create all those fascinating properties that different materials have. And understanding the periodic table is really not possible fully if you don't understand the protons, neutrons, and electrons. But that is not what this class is about. We're not going to rehash all of chemistry. That's not our job. and they keep going, right? Every time they say something is the smallest, they found something smaller, and we continue with that, right? So an electron is very, very small, a proton is very small, but we have gone further. We've smashed protons apart, and we've used particle accelerators to do that, and we have found that inside the protons and the neutrons are something called quarks, and that each proton and neutron is made up of 3 quarks, and these quarks have very unusual properties. This little picture here on the slide is of 2 ups and 1 down quark. They have very odd names as well. They appear to have mass but no size, but they do have charge. Very, very strange. Possibly another version of kind of the atom, right, where there's a lot of empty space inside the electron cloud and just a very tiny nucleus in the middle. Somehow protons and neutrons are made up of 3 objects that don't have size, but they themselves have size. It's very difficult for us to understand. Again, as we get very small, it becomes very hard for us to measure things and to collect data. And the less data we have, the less clearly we can see or we can understand the nature around us. But every time that we've thrown up our hands and said, oh, well, we're just not going to know, someone's come up with a way to gather that data and for us to know eventually. So sometimes we just have to shrug our shoulders and be patient and wait for a bright scientist to come up with a way of answering some of these questions that we struggle with. So moving on from the history, we're going to start talking about some of these characteristics. So what is the difference between solids and liquids and gases? Well, there's 2 ways to think about it, and it's oftentimes a bit of a combination of these 2 effects. But density and energy. So in a very general sense, and we'll speak about density later on in more detail in this chapter, but in a very general sense, the solids are more dense, the gases are the least dense, and the liquids are somewhere in between. Now, that's not an absolute, right? We have solid things that can float on top of a liquid, which means they are less dense than the liquid, and we'll go into the details of that calculation next chapter when we talk about fluids. But this is the general pattern. Most solids are denser than liquids. Most liquids are denser than gases, and that's one of the characteristics that separate them in different forms. And the other one also is energy. And so one of the principles we will cover next chapter, or next unit, when we get to chapters 14 and 15, is that as you put energy into atoms or molecules, as you heat them up, they tend to expand. So as they expand, they will take up more space, and that will make their density go down. So this idea that solids are densest and gases are least dense kind of goes in concert with this idea of energy. Solids tend to have less energy in them, and gases have more energy in them, and that's why they've spread out. Now, you got to be careful with that, right? Because there's different types of energy. Here we're speaking of thermal energy, which means basically gases tend to be hotter than solids. Obviously, you get some solids like coal or wood that have a whole lot of energy stored in their bonds, and we light them on fire, and they can release great amounts of energy compared to, say, a gas like carbon dioxide, which you can't burn and can't get very much more energy out of. So you got to be careful what type of energy you're talking about. Another important characteristic difference is going to be the fact that solids are actually bound to one another, right? So here we have this idea of a lattice where each solid molecule is somehow connected to those around it, versus a liquid where the molecules, they're pretty close to one another, but they're not connected. They're slipping and they're sliding past each other. And then in the gases where they are very spread out and running around and just occasionally bumping into each other, but for the most part, the molecules don't even know that the other ones exist. They are not affected. So as we start to talk more about the critical characteristics of solids, we need to keep this in mind, right? We can build things out of a solid. We can build a table or even just a stack of blocks if the blocks are solid, because there's this structure and we can stack them on top of each other. If you try to stack a liquid, right? If you take a cup of water and you pour it on the ground and you try to pour a second cup of water on top and a third cup of water on top, you will not get a tower. All the liquid will flatten out and create a giant puddle, and even more so with a gas. So it's this characteristic of solids that they are kind of stuck together in a structure, in a lattice that gives them their distinctly solid characteristics. And there's a little short video here, these Eureka videos, again, very helpful for our understanding. Little 5-minute video here on the structure of solids that can help us understand these characteristics. So again, the link is in the notes of the PowerPoint associated with this particular slide, and it's also in the description of this YouTube video if you're watching this on YouTube. So go ahead and pause my video and go watch this one, and then come back to mine. So these properties of solids, that they are bound together in a structure, allows them to have certain characteristics. And most of the characteristics we're about to talk about are only characteristics of solids, not of all matter. Like take this first one, for example, it's tensile strength. It's how strong is the material when you try to pull it apart, when you put it under tension. Tension is a pulling apart. Think about a rope. When you pull on a rope, the rope is in tension. It is being pulled by you, and it's being pulled by whatever's on the other end, anchoring it. If there's nothing anchoring it, then when you pull, the rope will just move. But when there's an anchor on both sides, the rope is pulled in both directions, and as long as the rope is stronger than you are, it won't break. But that's the principle here of the tensile strength, is we're going to pull the object until it breaks so that we can find out how strong it is. So they have this device in engineering schools and other places where they test the materials, and you see this green specimen. They make the specimen out of the material, and they make it a certain diameter so that they can pull on it, and when it breaks, then they can compare how much force it took to break it to what the cross-sectional area of the object is. I have a very distinct memory. When I was in college, I was living with another young man who was in mechanical engineering, and he had a class in which they were doing this, and they were learning about materials, and he would come home and he would show me these things that had broken, and he would show me the surface where it broke and explain all this cool stuff. And I smiled and I nodded because I didn't understand all of it, but it was extremely exciting to him. So tensile strength is an important characteristic. We look at it in different metals, different building materials. Interestingly enough, with all of our brilliant material engineering skills, we still can't quite get to the same level that spiders have, right? Spider silk is one of the strongest materials we know of in terms of tensile strength. The problem is that spider silk is very, very small. So it's very, very strong for its size, but it's very small. What we need is some giant spiders that can spin us some spider silk that's, tree trunk size, and then we would really be able to do stuff with it. And one of the things we would like to do is something that has very high tensile strength, is to create a space elevator, right? We talked a lot in recent chapters about getting into orbit and how difficult it is to get into space because of how fast you have to get going, and you have to ride on top of a rocket, and it takes a lot of energy and therefore a lot of expense. This idea that we could anchor a very long cable on the Earth and it could go all the way up into space, and then we could simply have a crawler that would crawl up and down this cable, and we would be able to get things into space by using our energy in a much more gradual manner, and therefore get there much more cheaply. But to do that, we have to have a material that's strong enough to be that cable for the space elevator, and that's going to require something that has very high tensile strength. Little image down here in the lower right of what they think a space elevator is going to look like. We don't have one yet. There are some companies working on it, but we don't have one yet. So tensile was pulling apart. Here we go the opposite direction. If we push it together, and we're going to talk about these more later, about how these two principles come together, the pulling apart, the tension versus the pushing together, which is sometimes called compression. Here they're just calling it hardness. And they have something called the Brinell test, where they smash the object until it breaks. Of course, it would be nice if they used the same format, right? The last one was force divided by area, which created, in fact, something we call a pressure. But here they do mass divided by area. So the units are different, and their chosen unit of area is the millimeter squared, which is not what we prefer. But again, this is a method and a industry standard that has been established by somebody who was not a physicist, but was an engineer. additional properties of solids, things like ductility and malleability. And this is how well the material can be worked, right? It's not, we are interested in materials that we can use to do things with. So ductility is being able to make it into a wire, right? And that's, of course, extremely important in our electronics age, where we want to be able to send electricity through a thin conductor. So can the material be made into a wire or not? And malleability, can it be hammered or rolled flat? Can it be shaped easily? And these two properties, interestingly, often go together in materials. And I spoke earlier of the periodic table of the elements and how there were different metals and different columns of metal. And there's that one column of just 3 metals, copper, silver, and gold. And they possess both of these characteristics, right? We have copper wires, we have silver wires, we have gold wires in very high-end materials. And so, and then we also have their malleability, right? They can be shaped into different shapes very easily. That's why they've been used as coins for thousands of years, because you could shape them into unique shapes, and they were relatively rare. Therefore, they had value in and of themselves. We continue to make our Olympic medals every 4 years out of these materials, again, because they can be shaped into interesting shapes and shaped how we want them to be. They are not all exactly the same, right? As you go down the periodic table, copper's the highest, and then silver, and then gold. One of the big differences between them is oxidation. How do they react with oxygen? Copper oxidizes very easily, especially in the presence of some degree of humidity. And the nice shiny, I was going to say coppery color, but obviously that's redundant to say copper is copper color. The orangish color of copper oxidizes into a green color. And so if you've ever had a penny, say, in the cup holder of your car, and some moisture gets in that cup holder, pretty soon you discover your penny has turned green. And of course, very prominent example, the Statue of Liberty in New York Harbor, sitting there in the middle of an ocean, in the middle of a harbor full of salt water, has oxidized long since, and she is no longer a orangish color, but a green color, because her entire outer covering is copper. Silver also oxidizes, or as we sometimes say, tarnishes, and turns a black color. So if you dig up old Roman coins or old English coins, or wherever you're digging up old coins, the copper ones will be green, the silver ones will be black. And when you dig up old gold coins, they are still gold, because gold does not oxidize. And that is also why gold is so sought after in high-end electronics as the connectors, right? Because if you have an electrical connection, and it's very important that the current and the resistance remain appropriate in that connection, you can't have any oxidation on the contacts, or else that will raise the resistance and cause a problem. So if you plate your contacts with gold, you don't have to worry about that issue. And because of the malleability of gold and because of the low oxidation of gold, that makes it ideal for this circumstance. So this is why gold is so valuable, because of its extreme practical applications. And so everybody wants it. So it's all about the rarity, right? Scarcity is what creates value in things. So another solid property is something called elasticity. Elasticity is often misunderstood, because the example that is almost always used for elasticity is a rubber band. And when people talk about a rubber band and elasticity, they're trying to focus on the fact that when you stretch a rubber band and let go, it goes back to its original shape. That's what elasticity means. But far too often people take that and they think that elasticity means the same thing as stretchy, but that is not true. So I have some different examples. A spring is elastic, and we will talk more about some spring examples in a little bit, but also a balloon is elastic, right? You can stretch the balloon, you can twist the balloon, and it will pop back to its original shape. But this is not the same as stretchiness, not at all. So silly putty, Silly putty is stretchy. Silly putty is not elastic. When you stretch silly putty and let go, it does not return to its original position. It just stays stretched out. So that's the difference, right? And the opposite of elastic simply means the opposite. It does not go back to its original shape, and or it cannot go back to its original shape. For example, an egg, once you drop and break an egg, it is not going to go back to its original position. Or, the children's story that we tell about Humpty Dumpty sitting on the wall, right? All the king's horses, all the king's men couldn't put Humpty together again. It does not go back to its original. It is inelastic. Even things that are elastic have something called an elastic limit. They can only be stretched so far before you exceed that elastic limit, and then it will not go back to its original shape. So again, springs are a great example of this. You can stretch the spring and it will pop back. You can stretch the spring and it will pop back. But if you stretch it too far, it won't go back to its original shape anymore. Another property we have to talk about is something called stress, which again is an engineering term. In physics, we tend to call it pressure rather than stress, although pressure can either be a push or a pull, whereas stress is always a push. So maybe that's the reason to have a separate word for it. But stress is applying a force over a certain area. So the stress is calculated by simply taking the force and dividing it by the area. And we measure this in units of pressure. Pascals are the SI unit of pressure. It's a very, very small unit of pressure. We're taking a single Newton and we're dividing it across a square meter. So imagine a square on the floor that's a whole meter stick by a meter stick. Remember, a meter stick is about the same as a yardstick. So a square that's a meter by a meter, and we're putting the weight of 1 Newton. Now, an apple comes out to be around 1 Newton, the weight of an apple. So you take the weight of an apple and you're spreading it across an entire 9-foot square space. So that's a very small amount of pressure. So the unit of Pascal is a very small unit. So we will be talking about tens of thousands, hundreds of thousands, millions of pascals, because they're just a small unit. The PSI is a much larger unit used in the English system, right? PSI stands for pound per square inch. So we're talking about a pound instead of a Newton, so we're a considerably larger force to begin with. And second of all, a square inch is way smaller than 9 square feet. So a PSI is a much larger unit. So when we get in subsequent chapters to discussing the pressure of the atmosphere, and we're going to say that it's 14.7 psi and it's 101,000 pascals, that's why those numbers are so different. They're describing the very same pressure, right? The atmosphere puts the same pressure on you at sea level, whether you're measuring it in pounds per square inch or in pascals. But because the pound per square inch is a large unit and the pascal is a small unit, the numbers we get are vastly different. So we have a little picture here of 2 bricks on a table that will try to emphasize what the difference is between this idea of stress or pressure and simply the idea of weight, right? Because those 2 bricks are the same. They're the same dimensions. You'll see that. They're 6 by 8 by 16, and they're made of the same material. But because they are sitting on the table differently, they provide different pressure. So we're going to call it a 50 Newton brick, but there's 2 different stresses, right? The brick A is laying on its side, so it has a lot of area exposed to the table. So its weight is spread out over a larger area. So its 50 Newtons are divided by 8 centimeters by 16 centimeters. I converted the centimeters into meters so that I could express my answer in pascals. So that gives me almost 4,000 pascals of pressure with the brick that's laying on its side. But the brick that is stood up on its end, it has 2 times, more than 2 times, actually more than 2.5 times as much pressure being exerted because it has a smaller surface area exposed to the table. So this is the whole principle behind anything that we ever use that is sharp, right? We have sharp nails, we have sharp knives, we have sharp scissors. All these things are designed to cut, and they cut because we apply the force over a very small area, and that causes the force to be delivered over a very tiny amount, and therefore the pressure is very high, and then you can cut things. So anything that is sharp is using this principle of pressure and stress. You can go the other direction too, right? Snowshoes are specifically designed to spread out your weight across a large area so that you put less pressure on the snow so that you don't sink in. So you can do it in both directions, but it can have some very extreme results. And this is why they talk about the fact that you need to sharpen your tools. And if you don't sharpen your tools, you're going to be putting a lot of force on it, and you're more likely to slip and cause a poor outcome. But if you have very sharp tools, then you don't have to use as much force to cut through, and then you have greater control. This is also, they have this great story about high heels, right? The heel of a high heel is going to exert very large amounts of pressure, because even though the person wearing the heels, it doesn't weigh very much, they're putting all that weight on a very, very small cross-sectional area. So they talk about the fact that if someone stomps on you while wearing a high heel, they can do more damage to you than an elephant stepping on your foot. And you sit there and go, well, but an elephant is very large. Well, an elephant is very large, much, much heavier than the person in the high heels, but the elephant has a large surface area to his foot that spreads out his force over a large area, and therefore the pressure delivered under an elephant's foot is actually less than that on the heel of a high heel. Obviously, depends on the elephant, depends on the high heels, but you can have that circumstance. So we've got the idea of tension that we talked about already. We have the idea of hardness, or what I called it compression, which is the squeezing together, pushing the atoms together from both ends. The tension is a stretch, the compression is a squeeze. And we understand that, right? And if we're talking about something vertical, we're going to have compression if it's being supported from below, and we'll see an example of that in a moment. But if you're being supported from below, if you have a stack of blocks, then the bottom block has to hold up the weight of all the blocks above it. Maybe you've never been a block, but if you've ever been a part of a human pyramid and you've ever been on the lower levels of a human pyramid, you're very aware of this, right? The people on the bottom level have to hold up the weight of everybody above them. The ground's pushing up on them, the people above are pushing down, they're being squeezed, they're under compression. On the other hand, if you have a vertical arrangement and the object is supported from above, then there is tension going on, right? If you hang something from the ceiling by a string or a rope or a wire, that string or rope or wire is being stretched by the weight that is hanging down from that string, and the other end of the string is attached to the ceiling, and so the string is being pulled apart, okay? And what we have found as we study materials is some of them are strong when you are squeezing them, and some are strong when you are stretching them, and very few are strong in both cases. But oftentimes they're strong one way or the other, but not in both directions. And so that dictates what we're going to build out of based on what forces we expect the object to experience. So that's all the vertical discussions, right? But what about the horizontal? What about this table in my picture that has a box in the middle and is supported on either end? That's causing my table to sag. So is my table experiencing compression, or is my table experiencing tension? That's the question. So if you look at the blue arrows that they have drawn, you'll see that sure enough, the bottom of the table is experiencing tension, right? I think of this, if the table was straight and now it's curving. So I like to think about a track outside of a high school, right? That you run around the track. And if you've ever looked at a track or run on a track, you know that the outside lane is longer than the inside lane because you're going around a bigger circle, right? You're at a bigger radius, bigger circumference, bigger circle. So as you make this table bend, you're making the bottom be the outside lane of the track, and you're making the top be the inside lane. So the bottom gets stretched and the top gets compressed. So we've got both compression and tension occurring in the object at the same time. But what is happening along the little dashed red line? What happens in the middle? If the top is squeezed, the bottom is stretched, you can think about the idea of an average. The center is going to be doing neither one. It's going to be pretty much the same as it was to begin with. And we have taken that principle, that idea that although the top experiences a lot of force in a compression, the bottom a lot of force and tension, the middle doesn't experience much at all. And that is what has given rise to the structural element that we call an I-beam, right? And we call it an I-beam because it looks like the letter I. And the letter I has a thick, strong thickness at the top and a strong thickness at the bottom, but in the middle it doesn't have very much thickness at all. And this is how they make I-beams out of steel or wood or other materials, and they're able to engineer them such that they can remove all that material, right? Instead of it being a solid, say, square block, instead you have an I shape to it. And you can remove a bunch of material, saving yourself a bunch of money from that material, and also saving yourself a bunch of weight from that material, and still maintaining a very high degree of strength. Because most of the strength that you need is actually in the top and the bottom and not in the middle. So that's where the I-beam comes from. That's why they shape them in that way, because of the compression and the tension you need on the top and bottom, but the fact that the middle basically just has to hold the top off of the bottom. So like I said, some examples. Concrete is extremely strong in compression, and therefore we build a lot of things that are going to experience compression, especially if they're experiencing only compression. We make it out of concrete. Concrete is very cheap. It's just basically rocks, sand, and a little bit of this cement stuff that we can mass produce. And so here you've got the pillars of a bridge. All the weight is on top of the bridge, pushing down on those pillars. They're not going to be stretched hardly ever. They're only going to be compressed. And so concrete is a great source, a great building material there. We think about sidewalks, roads that we're always going to be pushing down on, and therefore we make them out of concrete. Now, if you look at this picture and you look at the top of the picture, you can see there are steel I-beams making the, actual bridge portions of the bridge. And as we saw on the previous slide, when you have something horizontal across two supports, it's going to have to experience compression and tension. And so those I-beams are made of steel, which are strong in both directions and not just in concrete. So some other items with regards to solids. Again, solids we use to build stuff out of. They can experience compression and tension without failing. But we do have to consider some different things. One of them is the difference between live and dead loads. So a dead load is a weight that you have to hold up that's sitting still, but a live load is a weight that you have to hold up that is also moving. And I have a picture here of a frozen pond because I feel like that's one of the best examples of the difference between dead load and live load. Now I see this frozen pond and I might be brave enough to walk out on the frozen pond because I think the ice is relatively thick. But if I got out to the middle of the frozen pond and my friend back on the shore yells out to me and says, "Hey, why don't you do 10 jumping jacks? See how strong the ice is." I'm a cautious enough person that I'm going to say, no, I'm going to come back to the shore. You go out there and do the jumping jacks because the ice is holding my weight as I just stand on the pond. But if I were to do a jumping jack and jump off of the ice, I would turn myself from dead load when I was just standing there to when I come back down, I will be live load. I will be moving downward because of the acceleration of gravity, and the ice is going to have to stop me. It's going to have to deliver a normal force large enough to accelerate me in the upward direction so that I slow down and stop. And then that normal force is also going to have to be big enough to hold up my weight once I do stop. And so oftentimes the force necessary to stop something from falling can be 3 or 4 times as much as the force necessary just to hold it up. So this can also occur in buildings. If a building starts to collapse, it will often collapse in what's called a pancake fashion, where each floor squashes the one below it once they start falling because the dead load has turned into live load. There's a story about a library that was built once, where the architect building the library, or the engineer designing the library, he thought about the fact that it was a building, and buildings are heavy. He thought about the people that were going to be in the building. He thought about the furniture that was going to be in the building, but he forgot to calculate in the weight of the books in the building. And as a result, the building failed and began sinking into the soil, because books are very heavy and a library has a lot of them. So you got to consider all the different things that your structure is going to have to hold, even after it's built and once it's being used for its function. And there it was, sinking into the soil. Now we get another little short video to watch. This is of the Tacoma Narrows Bridge. It was built up in the state of Washington across the Tacoma Narrows. Again, there's a link in the PowerPoint notes and also a link in the video description, but this was a bridge that was built, and they failed to take an important aspect into consideration, and it was did not last even a year in its original configuration before what occurred in this video occurred. So I'll let you watch it, and then we'll talk about it a little bit afterwards. So what happened to the Tacoma Narrows Bridge is something called harmonic resonance. And this is something that you have to consider whether you're building a car or building a swing set or building a bridge. The fact that everything has a natural frequency that it will vibrate at. And if you vibrate something at that natural frequency, it will begin to move a lot. And as you saw with the bridge, it ultimately caused the bridge, which was made of steel and concrete, which have some elasticity, but not that much elasticity, to eventually bend and fracture and break and fall into the water. But harmonic resonance is easiest to think about, in my opinion, when you think about riding on a swing, particularly when you're little and you're not strong enough to pump yet, and so someone's got to push you on the swing. So you swing back and forth, and they give you pushes. And as you swing, you know, and the person pushing you knows that there's a certain time that they should give you a push forward, right? There's a bunch of times as you swing on the swing that they should not give you a push forward, because that would either knock you off the swing or slow you down or be unhelpful. But just as you swing all the way up to the back, and as you stop and you're about to go forward, that's when they should give you another push, and that will make you swing higher and higher. And they really don't have to push you very hard each time to reinforce your motion and get you to swing higher. And that's really what harmonic resonance is. And so as a designer, as an engineer, as a physicist, you have to examine things and make sure that we're not going to be driving resonance at the wrong frequency, which is the frequency that, you know, makes you swing higher and higher and higher, because we don't want the bridge to move more and more and more. We don't want the car to move, say, not move, cars are supposed to move, the vibration in the car. I had a car once and a road that I drove on a regular basis, and if I drove in the wrong lane and I drove at the wrong speed, my whole car would begin to vibrate, because of the motion and of the roadway in that particular area would reinforce the vibration and cause my car to vibrate. So you got to test things a lot of different ways when you build them. Tacoma Narrows Bridge's problem was it was very, very long, but it was also very, very narrow. And it had these big 8-foot tall solid steel I-beams on either side, which just caught the wind. And when the wind was blowing down Puget Sound at just the right speed, the wind would slam into the bridge and send a vibration through the bridge. And if the wind was blowing at the right speed, it would slam into the bridge again and reinforce that vibration. And that's what happened on that fateful day when the bridge collapsed. The solution, and they rebuilt that bridge pretty much right away. The solution was to make the I-beam not solid, to have holes in the I-beam so that the wind could go through and not deliver all its energy. And the Tacoma Narrows Bridge is fine today. They reuse the same towers, and people are still driving on it today. And if you Google Tacoma Narrows Bridge, the first thing you get is not a YouTube video of it falling down. The first thing you get is the traffic cams that watch the bridge, so that you can see whether there's going to be a lot of traffic on the bridge when you got to drive home tonight. Additional physical solid characteristics, one of them is shear. Again, we simplify things a lot in physics, and we've tended to this point have the simplification of the fact that objects are point particles, and whatever force is acting on the object is all acting on the same point. But that's not true in real life, right? In real life, objects have size to them. So here we have a phone book or an object that's being pushed one way on the top and another way on the bottom. And so the whole object is deforming because of those two forces. They're not simply canceling each other out. They're trying to deform the object and cause it to break, right? This happens very frequently. For example, when we have windstorms and you have signs along the highway and the wind hits the top of the sign and tries to push the top of the sign one direction, and the bottom of the sign is stuck in the ground, which is holding that part and essentially preventing the motion in the direction the wind wants to go. And you can snap the entire sign off if the wind is blowing hard enough. And that's called wind shear in that case. Torsion is just a special case of shear when we are rotating something. Again, as we talked about, there are two ways to rotate, clockwise and counterclockwise. And when you are twisting something like, say, this bolt in the picture, twisting it in or out of a material, there's going to be friction between the threads and the material, and so your wrench is trying to torque it one direction and the friction is trying to torque it the other direction, and if the screw itself is not strong enough, you'll twist the head right off of the bolt. And that's why as you get stronger bolts that are designed for a greater strength to hold more weight, you also end up with a thicker and thicker shaft, because it's not going to be able to hold thousands of pounds if the head can't take the torques necessary to deliver those kind of forces. Bending is another characteristic we have to deal with, right? Tension and compression together, as we talked about the table and the box on the table, and here we have a board and a person sitting on a board. Same idea that we're talking about, but how much is the bend going to occur, right? How much sag is going to occur when you have this situation? If we were in class, I would have brought my sponge and showed you the sponge and the fact that when your sponge is spongy and flexible, not all dried out and hard, when you bend the sponge, you can see the holes on the bottom of the sponge being stretched. You can see the holes on the top of the sponge being squashed together. You can kind of see very clearly this principle occurring with compression on top and tension in the bottom. So of course, they want to know how much bending you're experiencing. So they have another term they use, they call it strain, to measure just how much bending is occurring. And here it's just a simple ratio. How much vertically has your distance changed compared to how long are you horizontally, right? So how much sag is a very relative thing, right? If I'm sagging 2 inches and I'm only 6 inches long, that's a lot. If I'm sagging 2 inches and I'm 40 foot long, that's not a lot. So that's why we compare the ratio of how much is the sag divided by how long is the object itself. So now we're going back a little bit to this principle we talked about of elasticity, and we're looking at the mathematical expression, and it's called Hooke's law, not Captain Hook, a different Hooke, Robert Hooke. He was a physicist who lived about the same time as Newton, lived in England as well, and he wrote this principle of Hooke's law, and it's a very simple mathematical law. It's a direct relationship, and it simply says that the force necessary to stretch something or to compress something is equal to the elastic constant times how much you actually have stretched or compressed it. So if you apply twice the force, it will stretch twice as much. If you apply 4 times the force, it will stretch 4 times as much if it's an elastic object that follows the elastic law, which things that are elastic tend to do this. And again, elastic means it will return to its original shape. So if you pull the spring twice as hard, you'll stretch the spring twice as far. And when you let go, it will go back, right? The force will go to 0. And so the delta L will go back to 0 and the spring will spring back to its original shape. Now, as we already talked about, there are limits. And if you stretch the objects too far, then it won't return and it no longer follows Hooke's law. So here's just a couple of quick math examples for us to talk about. So we've got a very tight steel spring. Tight springs are going to have a large spring constant. So 35 newtons per centimeter. So to stretch it a 1 centimeter, it would take us 35 newtons. So what force is going to be necessary to stretch it a full 10 centimeters? So we just write out the Hooke's law, right? F equals K delta L. In this case, we're asking for the force, so we've already got it solved for what we want. So we can just plug in our numbers. Our K was 35 newtons per centimeter. Our delta L was 10 centimeters. The centimeter in the numerator and the denominator cancel. So we get 35 times 10, and we have newtons left over, which is what we would expect for a force. So we end up with 350 newtons necessary to stretch it 10 centimeters. Another example problem, what is the spring constant if 35 newtons will stretch it 20 centimeters? Again, as we do these actual problems in the notes, I would encourage you to pause and attempt the problem yourself before listening to my explanation. So we want the spring constant this time, so F equals K delta L. We're going to divide both sides by delta L to get the K by itself. So we'll end up with F over delta L on this side. So K equals F over delta L. The F is 15 newtons from the problem. The L is 20 centimeters from the problem. So that gives us 15 over 20, or a spring constant of just 0.75 newtons per centimeter. So obviously a much, much weaker, easier to stretch spring than the first one that was described. And finally, a steel beam. Steel is elastic, even solid steel is elastic. It doesn't seem very elastic because it has a very large spring constant, and we don't very often apply that size force in such a way that we can see the deformation and the return, but steel is an elastic material. Another interesting elastic material is golf balls. When you strike a golf ball, you cause it to partially collapse, and then it springs back out. So how far will 54 newtons bend a steel beam if its spring constant is 250 newtons per centimeter? So this time they gave us the force and they gave us the K, and they're asking for the L this time. So again, we want to find the delta L, so we're going to divide both sides by K. That'll drop the K out on this side and give us force over spring constant on the other. So the delta L equals force divided by the spring constant. 54 newtons divided by 250 newtons per centimeter. The newtons will drop, the centimeter will become our unit. And it's not very far, right? Barely over a fifth of a centimeter will it stretch because we're not using very much force, and it's a very resistant to being bent. So like we said, there's a limit to the elastic behavior, and here we have a graph that helps us understand that. So again, Hooke's law is a very linear relationship. So if you put force on the y-axis and delta L on the x-axis, then force over delta L, the slope of this straight line is the spring constant, right? And it's a straight line, and if you have the force, then you'll have your stretch. And if you triple the force, you'll triple your stretch. It's a very simple, predictable relationship until you hit the elastic limit, right? When you get to the elastic limit, it's no longer a straight line. It's no longer a linear relationship. Once you pass the elastic limit, then you reach a region they call the plastic region. And what I would like to point out here is you end up with a lot of stretching with just a little bit of extra force, right? So you really past the ideal circumstance for this material, and it's going to stretch out a lot until it finally fractures and breaks because you've applied too much force to it. So we don't have any physics in a first-year physics course that can handle the plastic region, so we are just going to use the Hooke's law in the elastic region, and if we get past that, we're just going to say, hey, we're no longer elastic. That's beyond our calculation situation. Stone was used for many, many years as the standard for compression. Still is. You still can go over to Europe and other places in the world and find stone roads that are very, very, very old, and they still are functioning perfectly fine. Stone is difficult to lift, and stone has limits when you go to do something like a bridge because there's tension as well as compression involved. So about the time of the American Revolution, there was a cast iron bridge shown here in this picture built in England, and that's when they began moving away from having completely stone bridges with stone arches that were extremely labor intensive, and trying to find new materials that they could use, like iron. Iron is nice, but iron is very prone to rust, and that's one of its great drawbacks. But we came up with other ways to modify the iron to make it into something called steel. And we've come up with ways to combine the tensile strength of steel with the compressive strength of stone, or artificial stone, concrete. So they create what they call pre-stressed concrete. And what they do there is they put steel rods in the concrete and they stretch them before they pour the concrete. And then they pour the concrete, let the concrete harden, and then they release the tension on the steel, and the steel basically squeezes the concrete and locks the concrete together. And that way, when something happens to actually stretch that concrete, the first thing that stretch has to do is undo the squeeze, the compression that the tendons are putting in. Because again, the concrete's very weak in tension, very strong in compression. But if you've already got it compressed, then the first however many thousands of newtons have to undo that compression before it actually starts stretching the concrete. We also just have generally reinforced concrete. That's when you put steel in the concrete to provide tension strength, right? And if you've ever seen them pouring concrete on a highway or in a driveway or many other places, they put that steel rebar or that steel mesh in the concrete to provide that reinforcement. So this idea of pre-stressed was done on the St. Louis Arch here locally, and there's again another little video, and the video is reasonably long. I only want you to watch a 2-minute portion, so make sure you take note of what part. And you can watch the whole thing if you want to, but if you watch this 2-minute portion, you will see how they pour the concrete between the skins of the arch, and then they use these steel tendons to do this pre-stressed process. So again, pause my video, go watch this video about how they built the arch and how they use this principle to make the arch stronger. So a couple of liquid properties that won't come up in the fluids chapter, because this isn't really about the fluid part of liquids. So there's cohesion and adhesion, and they're a little confusing because the words sound a lot alike. The last 75% of the words are exactly the same, and they have similar meanings too, right? Cohesion is that like molecules stick to one another, and adhesion is that unlike molecules stick to one another. So if you ever had any experience with molasses, it's a very sticky material. It's hard to scrape off of stuff because it sticks to itself so incredibly well. The molasses molecules stick to the other molasses molecules. On the other hand, glue is useful to us precisely because of its adhesion, because the glue will stick to something that's not glue. So you put some glue between the wood and the plastic, and the glue sticks to the wood, and it also sticks to the plastic, and it holds the wood and the plastic together, and therefore we have the connection that we want to have. But some very visual examples of this: water is very, very, very adhesive. It will stick to other stuff, not water, very much better than it will stick to water. So as you learned in chemistry, as you learned in grade school science, when you are measuring water, you get this weird U-shaped at the top of the water. They call it a meniscus, right? And it's U-shaped because the water is actually sticking to the sides of the test tube, the sides of the graduated cylinder. It's sticking to those sides, and therefore it's a little bit higher on the sides where it's sticking to the sides, and it's lower in the middle. And you get taught in science class that when you're measuring with a graduated cylinder, you're supposed to look at the center of the meniscus. That's the true level of the water that you're measuring. But if you look there in this central picture, The water has a U-shaped meniscus, but right next to it, we have a test tube partially full of mercury, and mercury has an upside down meniscus. It is humped in the center and lower on the edges, and that's because mercury has greater cohesion. The mercury molecules want to stick to other mercury molecules. They don't want to stick to the glass on the side, and so they clump together in the middle and create an upside down U. I'm not sure how you're supposed to measure mercury if you've got it in a graduated cylinder. They don't let me play with mercury. It's considered too dangerous these days. I would assume you still read it from the center. And then the picture in the lower right, you see those are drops of mercury on a glass tabletop, and mercury forms much more distinct droplet spheres than water does, right? You drop a couple of drops of water on a surface and it's going to flatten out, trying to adhere to the surface and create a flat puddle. But the mercury would rather cohere, stick to itself, and so you get these more distinctive droplets of mercury, which are really fun to play with if you ever get a chance, but don't eat them. They're toxic. Other liquid properties, surface tension and viscosity. Surface tension is kind of what it sounds like. There's tension on the surface because there is a surface there, and we're not going to go into the details of why that is, but on the surface there is this tension that's enough to support weight. As you see in that little picture, there's a spider on the surface of the water, and it's not that that spider is floating. We'll talk about what floating is next chapter with fluids. That's a different thing. A spider is actually standing on the surface, even though he's heavy enough to sink. He's standing on the surface because of the surface tension. And the way you can tell the difference, if you have something on the surface of the water and you're not sure whether it's floating or whether it's sitting on the surface tension, is that the characteristic of surface tension in water can be destroyed if you put just a little bit of soap in the water. That will break the surface tension. And so again, if we were together, I would have this wonderful little example with a baby food jar and a paper clip, and I'd set the paper clip on the water, and you would go, oh, the paper clip's floating. And then I put just a tiny drop of laundry detergent on the surface of the water, and the paper clip sinks because I've broken the surface tension and it's no longer able to maintain its position. Viscosity is the internal friction in a material due to the cohesion. So we talked about the fact that molasses really sticks to itself. And in the process control world, this is a really big thing, right? Crude oil has a fair amount of cohesiveness as well, and different products do or do not. And so it's the internal friction due to the fact that the stuff sticks to itself, and therefore it's going to resist the smooth flowing. And this viscosity can be dealt with heat. As you heat the material up, you make the molecules move faster, they slide past each other easier. So you can lower the viscosity by raising the temperature of the material, the fluid that you're dealing with. Viscosity, I don't like viscosity because to me it's backwards. Higher viscosity means more friction. But when I hear viscosity, I think about flow, and higher viscosity does not mean higher flow. Higher viscosity means less flow. Viscosity is resistance to flow. So I just think the definition is backwards. So I've never liked that term, but that is what it is. Viscosity is the measure of internal friction. So more viscosity, less flow. Molasses, lots of viscosity. Water, very low viscosity, right? Water does not have much cohesion, so water will flow very easily through the pipe. Not true of all the petroleum products. So last thing we're going to talk about here is the idea of density, and we will go more into density next chapter. It's extremely important when you talk about how you discuss whether things float or not. But we're going to introduce the principle here and the formula here to give ourselves a little practice ahead of next chapter, because it is also a physical property of solids and all matter for that matter. So density is how much stuff, how much material you have per volume, okay? It's not how heavy you are, it's not how much space you take up, it's a combination of those two things. And again, we got a short little Eureka video that does a good job, I think, of driving home the difference between mass and volume and density. So pause the video, go watch that Eureka video, and then come back here and we'll say a couple more things about density. One of the great visual examples of the difference in density is to think about something like styrofoam compared to lead, right? Styrofoam and lead are the two opposite ends. Lead has a very high density, and so you can get a very heavy amount of lead in a small space, whereas styrofoam is really mostly air, and so you get a very large amount of styrofoam, and it still doesn't weigh very much because its density is very, very, very low. Density gets to the heart of that famous question, right? What weighs more, a pound of feathers or a pound of bricks? And people tend to say, oh, well, a pound of bricks, because when you hear what weighs more, you tend to think about density. You tend to think of the same volume. But the reality, of course, is that a pound of feathers and a pound of bricks both weigh a pound. But a pound of feathers is going to take up a lot more space because feathers have a lower density. The other thing you need to appreciate about density is it has nothing to do with the amount that you have. Density is a characteristic of a particular material, and it doesn't matter how much you have. Whether you have a lead cannonball, or whether you have a lead bullet, or whether you have a lead BB, they are all going to have the same density because they're all solid lead. You just be dividing, a smaller mass by a smaller volume, you're going to get the same ratio. Divide a big mass by a bigger volume, you're going to get that same ratio. The same thing with water, right? Water is water. Whether you have a glass of water or a swimming pool of water or all of Lake Michigan of water, it's still going to have the same density. You have twice as much mass, but you also have twice as much volume. Or you have 10,000 times as much mass and 10,000 times as much volume, you're still going to get the same ratio, right? 600,000 divided by 100,000 is 6, and 0.6 divided by 0.1 is also 6. You get the same ratio. What does make a difference density-wise, and where density can change, is when the object is full of or has in it air. Now we'll talk more about that next chapter, about how liquids are not compressible and gases are. But if you take something like this last picture I have here, a dinner roll that's just come out of the oven, right? You can measure its volume, you can measure its mass, you can get a density. But if you take that dinner roll in your hand and you just crush it, you're going to make the volume smaller and the density is going to stay the same, right? This is what they talked about in the car crusher machine on the Eureka video. They were basically squeezing the air out of the cars, and therefore they were making them denser. You can think about a stress ball, right? That's what you're supposed to do with a stress ball, is squeeze it and crush all the air inside. And when you do that, you make the stress ball denser. So understand the fact that objects that have air in them, their density can be, or any gas in them, their density essentially can be modified by applying force so that that gas gets compressed, because that changes the volume of the object without changing its mass. Can't do that with a solid lead cannonball, right? If I cut the lead cannonball in half, I can make a half ball that has half the volume, but it's also going to have half the mass. So here's the equation, and it's a little bit confusing because there's two types of density. I wish there was only one. I wish nobody ever did it the other way, but the reality is people do. So mass density is the one I think of. Mass density is the one I think is most useful and most meaningful. It's how much mass do you have per volume. So it's just mass divided by volume equals density. Kilograms per liter, kilograms per cubic meter, kilograms per cubic centimeter, grams per milliliter per cubic centimeter. It would be a unit of mass divided by a unit of volume. But there are also examples in the book, examples in real life of people who simply do weight density, right? We talked about the difference between mass and weight. Your mass times the acceleration of gravity equals your weight. So if you have the weights more readily available than the masses, then you go, well, I'm in a hurry. I'm just going to do the weight divided by the volume instead of dividing my weight by gravity to get the mass. So there's something called weight density. You notice how I distinguished them with a subscript, D sub M for mass density, D sub W for weight density. You really have to look at the information that they've given you to make sure that you know which one you're dealing with. And you just have to be comparing apples to apples, basically. You gotta be doing the same thing both ways, and make sure that if you're not solving for the density, if you're solving for an answer, that you label your mass or weight appropriately when you get your answer. So gold's a pretty dense material, 19.3 grams per milliliter. That's 19 times denser than water. If you had a volume, what would the volume be if you had a 1 kilogram bar of gold? Now you can sit there and compute how many ounces a kilogram is and find out that a 1 kilogram bar of gold would be, nearly equal to my annual salary. But that's not really the question. The question is, what is the volume of a 1 kilogram bar of gold? So we are given a mass density, so we're going to use the mass density equation, mass divided by volume. We are asked for the volume, so we're going to bring the volume to the other side, multiply both sides by volume, and then divide both sides by the mass density. That'll get us the volume by itself, and mass divided by the density on the other side. So 1,000 divided by 19.3 yields us just 52 milliliters, or 52 cubic centimeters, a very small cube that's only a little over 3 centimeters on a side. So it doesn't take very much gold to be worth a lot of money, which is why, back in the day and even today, people leave normal life and go searching for gold, because you don't have to find very much to be rich. What is the mass of 2 liters of water, right? Soda is mostly water. And so what would the mass of a 2 liter of water be? Remember, the density of water is 1 gram per milliliter. In fact, that is part of how they defined some of those units, so that we would get a perfect ratio of 1 for water, because water is so important in our everyday life. So what is the mass of 2 liters of water? So density, again, mass density, we've got mass divided by volume. This time we want to know the mass, so we multiply both sides by the volume to get the mass by itself. So now we have the mass density times the volume equals the total mass. 1 gram per milliliter times a liter would be 1,000 milliliters. So 2 liters would be 2,000 milliliters. 1 times 2,000, milliliters drop, we get 2,000 grams, or 2 kilograms. And again, with kilogram being approximately 2.2 pounds, we're talking about a 2 liter being about 5 pounds. So if your 5-pound dumbbell has disappeared, you can just try doing curls with a 2 liter of unopened 2 liter of soda instead, get the same effect. So here's a chart from your book of densities of various materials. And I just want to take a moment to point out here the discussion that we had way back at the beginning of the chapter of solids versus liquids versus gases. So here you see, and which units you choose it doesn't matter, right? We're comparing as long as we stay in the same column. So kilograms per cubic meter, right? A cubic meter is a very large volume. It's a meter stick by a meter stick, a box that's a meter stick high and a meter stick wide and a meter stick long. So these are large numbers, because that's a large volume. But you see here the solids, they're almost all in the thousands of kilograms per cubic meter. A few are not, right? Cork, we know, is a very light solid, mostly full of air. And there are some woods that are lighter, but most of these are in the thousands of kilograms per cubic meter. And then we come down here to the liquids, and most of the liquids are less than that, right? They're in the hundreds of kilograms per cubic meter. Seawater, water are both right at 1,000, but they're generally in the hundreds. Okay. Mercury is the exception. It's a very, very dense liquid. It's actually a metal, and we'll talk about that more a little bit later, how we use that particular special heavy liquid in certain circumstances. But you see here the solids are generally a little bit, not a ton, but a little bit denser than the liquids. But then we come down here to the gases, and the difference is huge, right? So we talked about solids that were thousands, liquids that were hundreds. Now we're talking about gases, which are single digits of mass per a cubic meter. So we're talking 100, 1,000 times less dense than either of the other two that we were discussing. And so that's going to be a big deal, especially next chapter when we start talking about things floating in a liquid versus things trying to float in a gas like the atmosphere, how it's just a totally different scale that you have to get after in order to appreciate that. You'll also notice here amongst the gases, air is the one that we're most familiar with, right? But so as we start comparing other things with air, we discover that carbon dioxide is denser than air. So carbon dioxide will sink, right? So if you have carbon dioxide in your garage, it's going to form a layer on the floor. Versus carbon monoxide is less dense than air, and it will rise, and you will have issues near the ceiling with your carbon monoxide. Helium and hydrogen are both much, much less dense than air, and that's why we can put them in balloons, and the balloon, even though it has more dense plastic skin, will be able to float in the air. So one issue with finding the density of something is, what if it's not a nice, pretty rectangle or cube or sphere or cylinder? What are you supposed to do? What if I want to find the volume of my handy dandy little toy Tyrannosaurus Rex, right? What am I supposed to do? He's not a cube, he's not a rectangle, he's not a sphere. How do I find his volume? Because without his volume, I can't find his density. So one principle is the principle of displacement, right? So we drop him in the graduated cylinder. We see that it was reading 4.8. We drop him in, now it's reading 5.6. So we subtract those and we know what his volume is. If he doesn't fit in the graduated cylinder, we have these large objects, basically overflow containers. So you fill it up with water until the water starts running out of the spout, and then you stop filling it up. Then you put an empty measurement container under the spout. You put your large object in. However much water has overflowed has been displaced by your large object. Even if your large object is very irregularly shaped, the volume of water in here will match the volume of your object. So this is the principle of displacement, which again, come up big time when we talk about buoyancy next chapter as well. There's also this thing called specific gravity, which they like to use in the process control world. They also like to use in the dairy world. It's about trying to figure out the density of particularly liquids, which is not always the easiest thing to do. And so there's this device called a hydrometer. And what it's going to do, you stick it in a liquid and it's going to float at a certain level, and it's going to tell you the specific gravity of the liquid. And specific gravity is just a fancy way of saying what is the ratio of this material to the ratio of this material's density to the density of water. Because again, water is so important in our world, and it has a density of 1. And so if you compare it to water, then you know what it's going to be. So that's what specific gravity is going to be. So again, it's a very simple thing because water's density is 1, and it's a shortcut to be able to make this comparison. So anything that has a specific gravity of more than 1 is going to have a density more than water and is going to sink in water. Anything less than 1 is going to float on top of the water. So again, they use it in the dairy industry to measure the fat content of the milk. And they use it in process control, of course, to try to identify which product that you're dealing with. All the different distillants out of crude oil are going to have different specific gravities as well. So that is the end of chapter 12. We will be back for chapter 13 next time.